Swayam Prabha. Digital India. Educated India.
Namaskar. So, in last class we were discussing about the state diagram. Today we will discuss about the state transition matrix. So, let us start the discussion of today's session. So, before going into the state transition matrix, let us first understand how you will create the state and output equations from the state diagram. Now, you may be knowing that the state equation and output equations can be obtained directly. So, with the help of a state diagram, state equation and output equation we know, we have discussed in the previous lectures. So, we will see today that how state equation and output equations can be obtained with the help of state diagram. For that we use signal flow graph gain formula and find out the state and output equation. So, what is state equation? Let us recollect what we discussed in previous lectures. So, state equation is nothing but dx by dt is equal to ax plus br. This can also be written as x dot. So, this particular equation is called state equation. Then output equation can be written as, say, yt is the output. So, you can relate the output with the states with the help of output equation. So, this will become yt is equal to cxt plus drt. Now, what is xt? Xt is the state variable and rt is the input and yt is the output. Here you will see that a, b, c, d are the constant coefficient. So, in this way you can define the state and output equation. Now, let us try to find out the procedure of deriving the state and output equations from the state diagram. So, in the state diagram you have seen that there are initial states and integrator branches in addition to the gains which we connect from one node to other node. So, when we derive the state and the output equation from the state diagram, we first delete the initial states, that is we say like time t is equal to 0 or maybe any other time, say t naught. What are the initial states? We will remove those initial states from the state diagram. We also remove the integrator branches which have gain as 1 by s from the state diagram. Why we remove it? Because the state and output equations do not contain the Laplace operator, that is s or the initial states. So, that is why we remove these two components from our state diagram. Now, for the state equation we find the nodes that represent the derivatives of the state variables as output nodes. So, this will become the left side of the state equation, and then the output yt will also be identified. In the output equation we will represent yt, that is naturally an output node variable in the state diagram. Now, next we will identify the state variables and the inputs as input variable on the state diagram, and these variables are found on the right side of the state as well as output equation, and then we finally apply the signal flow graph gain formula to the state diagram. Let us take one example so that we can understand how we can find out the state and output equation with the help of a state diagram. Let us see, this is the state diagram where we have removed the initial states as well as the 1 by s, that is the integrator section. So, we are left with the only gains and the states. So, if you see here r is the input, it is going into the state. Let us say this is the x2 dot given in the state diagram, x1 is connected to y. So, from here you can straight away say that y is nothing but equal to x1 t. So, this will give you the output equation. Now, let us try to find out the state equation. So, when you see this particular node, x2 is nothing but x1 dot. So, what we can say, x1 dot is nothing but dx1 by dt. So, we get one equation as dx1 by dt is equal to x2. Next node we have x2 dot. So, from here x2 dot is nothing but dx2 by dt. How it is linked with other states? So, if you see the state diagram, you can say that x2 dot equal to minus 2 x1 minus 3 x2 plus RT. So, when you apply the summation at this point, you will get the another equation. So, you got these two equations, this you can write as x1 dot. So, if you see this, you can compile this as x1 dot x2 dot in the matrix form. So, for this, since we do not have x1 component, first will be 0, then you have x2. Here you have minus 2 of x1 and minus 3 of x2. So, you will get this plus RT is in the second one. So, you can just compile and you write it as RT. So, this is x1 t, x2 t and 0 to 1 RT. So, this is how you will get the state equation from the state diagram. Output equation we have already seen, that is yt is equal to x1 t. So, this is how you compile the state and the output equations. Now, let us talk about the state transition matrix. What is a state transition matrix? So, here in the previous slide we have seen the state equations of a linear time invariant system are expressed in this form. So, dx by dt is nothing but x dot. So, dx by dt is equal to axt plus but. Now, the next step is the finding out the solution of this equation. Let us assume that there is an initial state vector x t naught and the input vector we have ut for time t greater than 0. Now, if you see this particular equation, the right hand side of the above equation is known as homogeneous part of the state equation, and next term is forcing function, that is ut. Now, if you assume for the time being that ut is 0, then we have homogeneous equation. So, homogeneous equation is nothing but dx by dt is equal to a into x t. Now, let us assume that there is a matrix phi t which is n cross n matrix and it represents the state transition matrix. So, in that case, if it is the state transition matrix, it should satisfy the following equation, that is d phi by dt is equal to a phi t. Now, if x naught denotes the initial state at time t is equal to 0, then phi t can also be defined in the matrix equation, and you can write it that x t is equal to phi t into x naught. So, state transition matrix is nothing but the matrix which correlates any the state at time t is equal to 0 to any state of time t. So, this equation which you have got x t is equal to phi t into x naught is the solution of homogeneous state equation. Now, we need to find out the value of phi t in terms of the other parameters which we have, like we have a, b and x. So, what we will do, the value of phi t can be determined by taking the Laplace transform on both sides of this equation, that is the homogeneous equation we have got, that is dx by dt is equal to a x t. So, when you take the Laplace transform on both sides, what you can write? For this side you can write s into x s minus x at time t is equal to 0 is equal to a x s. Now, if you rearrange the terms, you can simply write xs is nothing but s into I is a identity matrix minus A inverse x at time t is equal to 0. So, this is what you get the value of xs. Now, if you see, we are taking the inverse of this matrix, that is Si minus A. So, the important property which we have to assume here is that the matrix Si minus A is non singular, means the determinant of this particular matrix is not equal to 0. Now, let us take the inverse Laplace transform on both sides. So, the equation what we have is xs is equal to Si minus A inverse x naught. So, if you take the inverse Laplace transform x t, then the inverse Laplace transform of this and x 0, which is the constant quantity for time t greater than 0. Now, this you can compare with our initial equation which we found in terms of a state transition matrix, that is x t, that is the state at any time t is related to the initial state with the help of state transition matrix. So, when you compare both of them, you can simply get the value of state transition matrix, that is phi t, as inverse Laplace transform of Si minus A inverse. Now, what is the significance of a state transition matrix? As the state transition matrix satisfies the homogeneous state equation, it represents the free response of the system. Free response means the response that is excited by the initial conditions only, keeping the forcing function, that is ut equal to 0. Now, in view of previous equations which we have just seen in the previous slide, the state transition matrix is dependent only upon the matrix A. So, if you see this, the state transition matrix is depending upon the matrix A, that is why sometimes it is referred to as the state transition matrix of A. Now, as the name applies, you see the state transition matrix. So, the state transition matrix completely defines the transition of the state from the initial time t is equal to 0 to any time t when the inputs are 0. So, this is one of the most important property of the state transition matrix, because with the help of this we can completely find the value of x at any time t given the initial state, that is state at time t is equal to 0. Now, let us talk about the state transition equation. So, the state transition equation is defined as the solution of linear homogeneous state equation. So, the equation which we have linear time invariant, that is dx by dt is equal to ax plus bu, this is the state equation we have. Now, the above equation can be solved using either the classical method of solving the linear differential equation, or we can utilize the Laplace transform. So, if you use the Laplace transform, the above equation you can write in Laplace domain as the dx by dt you will become s xs minus x at time t is equal to 0 is equal to a xs plus b u s. So, x at time t is equal to 0 denotes the initial state vector evaluated at time t is equal to 0. Now, if you solve for xs this particular equation, what you get? You get the Si minus A inverse into x at time t is equal to 0. This is what we saw in case of state transition matrix, plus Si minus A inverse B u s. Now, the state transition equation you can obtain from this equation with the help of taking the inverse Laplace transform on both sides. So, here now you get the value of x t is equal to inverse Laplace transform of Si minus A inverse x 0 plus inverse Laplace transform of Si minus A inverse B u s. So, this term you have got in addition to the term which we saw in case of homogeneous output, homogeneous response of the system, because now you have added the forcing function in the system. So, what you can write now? You get this term, nothing but the state transition matrix, and then you get x at time t is equal to 0. So, you get phi t x 0 plus the inverse Laplace transform of this component. So, we will use the fundamental theorem of inverse Laplace transform. You can write this as integral 0 to t phi t minus tau b u tau d tau for any time t greater than 0. So, this is what you got the state transition equation, that is the output x t when you have forcing function present in the system. Now, this is what we have defined when initial time is defined at time t is equal to 0. Now, if initial time is say any other time t naught, the corresponding initial state will now become x t naught, and we assume that there is an input, that is u t, which is applied at any time t greater than 0. So, if you put t is equal to t naught in the previous equation and simplify, you will get now x t is equal to phi t minus t naught x t naught plus 0 to t integral phi t minus tau b u tau d tau. Now, once the state transition equation is determined, the output vector you can express as the function of initial state and the input vector simply by substituting x t into the output equation. So, what is the output equation? We have output equation as y t equal to c x t plus d u t. So, the output which you will get is y t is nothing but c, in place of x t you write the output which we just derived, that is x t. So, we can write now y t is nothing but c into phi t minus t naught x t naught plus 0 to t c phi t minus tau b u tau d tau plus d u t. So, this is what we get the output equation for the system where the input is available. Now, let us take example and try to find out the state transition matrix first. So, let us consider the state equation, that is say dx1 by dt, dx2 by dt, or you can simply write as x1 dot and x2 dot equal to the matrix A into the state vector, that is x1 t x2 t plus b u t. So, when you compare this with equal to a x plus b u, you will get the value of a and b. So, you can simply compile the value of a and b. A will be 0 1 minus 2 minus 3, b is 0 1. So, now we have got coefficient matrices. In the question it is given that u t is equal to 1 for t greater than or equal to 0, that is why this is 1. So, now we need to find out first the state transition matrix. So, what will be the state transition matrix? First, let us try to find out the value of S I minus A. So, when we get the value of S I minus A, we get S minus 1 into S plus 3. Now, inverse of S I minus A will be as shown in the slide, that is 1 upon S square plus 3 S plus 2. In the matrix, the component would be S plus 3, 1, minus 2 and S. Now, the state transition matrix you can find by taking the inverse Laplace transform of this. So, when you take the inverse Laplace transform, what you get? You get the matrix having component 2 e to the power minus t minus 2 e to the power minus 2 t. Then next is e to the power minus t minus e to the power minus 2 t. Third component is minus 2 e to the power minus t plus 2 e to the power minus 2 t, and fourth one is minus e to the power minus t plus 2 e to the power minus 2 t. So, this is simply you can get by taking the inverse Laplace transform of the matrix. Now, the state transition equation for t greater or equal than 0 is x t is nothing but phi t, x at time t is equal to 0 plus 0 to t phi t minus tau b u tau d tau. Now, the value of state transition equation for t greater than or equal to 0 is obtained by, you have found the value of phi t. Now, b is given, ut is also given in the question. So, when you put all those things, you get the state transition equation. So, that is the phi t multiplied by x at time t is equal to 0 plus you have the integral component. So, you take phi t minus tau into b into u tau, and when you simplify and take the integral, you will get the vector as 0.5 minus e to the power minus t plus 0.5 e to the power minus 2t, and the second component will be e to the power minus t minus e to the power minus 2t. So, this is the state transition equation which you will get for any time t greater than 0. Now, let us see the relationship between state equations and the high order differential equation. So, let us consider one differential equation. So, that is the third order equation, you have d 3 y by d t 3 plus 5 d 2 y by d t 2 plus dy by dt plus 2 y t is equal to u t. So, this is the higher order differential equation is given. We need to find this, we need to convert it into the state equations. So, first thing what we have to do, we have to first rearrange the equation by setting the highest order derivative term to the rest of the terms. So, if you take this on the left, so this will become d 3 y t by d t 3 is equal to minus 5 d 2 y by d t 2 minus dy by dt minus 2 y t plus u t. Now, let us define the state variables. So, first state variable we define as x 1 t is equal to y t, then next is x 2 t is equal to dy by dt, or you can simply write equal to x 1 dot, because this is nothing but dx 1 by dt. Similarly, x 3 t is nothing but d 2 y by dt 2, or you can write as x 2 dot. So, what you have got now, x 1 dot equal to x 2 t. So, that is the first equation you have got. Second equation which you have got is x 2 dot t is equal to x 3. So, this is what you have got from these two state variable definition which you have defined. So, you first defined x 1 as y t, then x 2 and x 3 are nothing but dy by dt and d 2 y by dt 2. So, this has become now x 1 dot and x 2 dot. So, you have got these two. Now, next is we need to find out x 3 t dot, x 3 dot is nothing but d 3 y by dt 3, because you take the derivative of this again, you will get d 3 y by dt 3. So, if you see x 3 t dot is nothing but equal to this equation. So, what you can write, if you compare x 3 dot is nothing but equal to minus 5 d 2 y by dt 2, minus 5 d 2 y by dt 2 is nothing but x 3, then minus dy by dt. What is dy by dt? dy by dt is equal to x 2, and then minus 2 y, 2 y is nothing but minus of 2 x 1, then plus u t. So, this is the third equation you have got. So, these are the three equations which are nothing but the state equation, because these the differential equation you have now decomposed into the state equations. So, this you have got. Now, what the next is? Next is you have to just compare the standard state equation, that is dx by dt is nothing but ax plus bu. So, dx by dt in this case is x 1 dot x2 dot and x3 dot. So, then equal to a into xt. So, a into xt means here xt is nothing but x1, x2 and x3. So, this you have, then plus b u t. Now, what is the value of a? If you see these three equations which you have derived, you can simply find the value of a. Here x1 component is 0, so you will get 0, x2 you have coefficient as 1, there is no x3 component, so you have got again 0. For x2 dot, x1 and x2 are not there, so you have 0, x3 is present, so you have a coefficient as 1. Now, next is x3 dot. So, here the x1 is minus 2, x2 is minus 1 and x3 is minus 5. So, this is what the value of a you get. So, you have got now the value of a, which is nothing but 3 cross 1 3 cross 3 matrix corresponding to xt, which is 3 cross 1 vector. Now, what is the value of ut? If you see again these three equations, u is not present in first and second equation, it is present in only third equation. So, b will become now 0, 0 and 1. So, you have got now b as 0, 0, 1. So, using the state equation representation, you have converted the differential equation into the state equation. So, here you have got x1 dot, x2 dot, x3 dot as the left side, that is dx by dt, plus a you have now calculated, then xt is the state vector which is having components as x1, x2, x3, then ut, that is the input. So, b corresponding to ut you will have as shown in the slide, that is 0, 0, 1. This is what we have also computed. Now, the equation you have just compiled. Next is we need to find out the output equation. So, if you see this particular equation, that is x1 t is equal to y t, we have considered y t as an output, because this is what you will get when you solve the differential equation. So, if you solve, you get y t in terms of the other components. So, y t is considered as a output variable. So, this will be considered as a output equation. So, if you see this, you have considered as an output equation. Now, if you write in matrix form, you can write this as 1 0 0 into x t. X t is nothing but x1, x2, x3 vector, and this is the c c vector, which is 1 0 0. So, when you see this particular equation and you compare with what we have in terms of output equation, that is you get Cx plus du. So, if you see this equation, the u component, that is the input component, does not come into the picture. So, that is why u will be absent, and finally, the value of y t you will get is only the c and x vector. So, c we have as 1 0 0, because you have only output related to x1, that is first state variable. So, you can write c as 1 0 0 and then the state vector x. So, this is how you get the output equation. So, with this we can close our today's discussion, in which we discussed about the state transition matrix as well as the state transition equation. Thank you.